In class, hope everybody's doing fine. We are looking at 1.5 inverse functions and laws. We have covered 4 ways of representing a function, mathematical models, new functions from old, exponential functions, and now we're going to move on to the new section, inverse functions and laws. We recall from 1.3 as far as the algebra of functions, composite functions, and old functions from the new functions, in other words, transformations, how they look like. Some formulas for exponents, exponential rules were discussed, and then the exponential function. And the main thing to remember, the base is either larger than 1 or between 0 and 1, because if it's equal to 1, it is not an exponential function. So we're going to go to the new stuff now. Okay. And so let's get started by putting it in a slideshow. All right, we are going to look at some definitions we have seen. There is not much brand new, everything is posted, so I want to go over this pretty fast. This is the synopsis of inverse functions. First, a function can have an inverse if it's one-to-one. So what is the definition of a one-to-one function? I remind you of the definition of a function. In short, x couldn't repeat. It would become a function. Now the y cannot repeat either. So a one-to-one function is that if the y's are different, so are x's. That's the idea. And we had a vertical line test to test whether a graph represents a function. Now we have a horizontal line test. A function is one-to-one if and only if no horizontal line intersects the graph more than once. Okay. So that is something we have seen. Now, by definition, when we write the inverse function, their domain and their range interchange, okay? So when we say f inverse of y equals x, it's the same as saying f of x equals y. Their composite function is equal to x, okay? X and y. With the f function, we map x into y, and with f inverse, we reverse the process, okay? So if f maps x into y, then f inverse does the reverse process, maps y back into x, okay, class? That's the synopsis of that. Now, if we look at it from a function machine point of view, take a look at what happens. When you enter the x into the f of x machine and then into f inverse, they undo each other and we get x. And this has a lot of applications, for example, encryption. So if you happen to put a number in here, class, instead of x, okay, that is, let's say, the first digit of your credit card number, then when they claim it's a secure environment, then f of x immediately changes it and nobody can see what's the original number. In between, maybe somebody grabs it, but it doesn't matter. At the end, when it goes back to the company with the f inverse, they change it, and again, they get the same digit back. Now, if two functions are inverse of each other, their composite function is x. Okay, so this is the synopsis of the section as far as inverse functions is concerned. And these definitions are repeating again, and this horizontal line test that was discussed, so there's really nothing brand new. We are repeating the previous page in essence. So is this function a one-to-one? In order to see whether a function is one-to-one or not, one is, of course, you can graph it and you look at the graph and horizontal line test, okay? The other one is that if x1 and x2 are different, the result must be different. There is, no way to come up with two numbers that have the same cube. And in order to prove otherwise, all you have to do come up with one pair. For example, If f of x equals x squared, you can easily see that's not the case, because if it's positive and negative value of the same number, f of x becomes the same. So that's how you unprove something. Of course, the graph and a horizontal line test will do that for us. So that's very straightforward. The next thing I want to look at, again, we're going to repeat the stuff that we have seen in the summary, okay? Two functions are inverse of each other. Look at the function machines, one after another, and what happens. Look at the composite function that was discussed. A very simple example, we just looked at x cubed. So what is its inverse? Okay, it's x to the power of 1/3 or cube root of x, and we will go through the process of finding that. We'll see how it is found. But in the meantime, if that is the case, and somebody says, okay, these are the two functions, are they inverse? And you claim they are inverse function, you have to prove by looking at their composite function. So if you look at, and you don't have to do both, but it's a good practice to do both. So if you find f inverse OF or f OF inverse, either one makes no difference, should give you an x. Now, how do you find the inverse function? There are really a couple of methods. Ultimately, they become the same. One of them is you change the f of x to y, okay? You solve this equation for x in terms of y, and then you change the y into f inverse. What do we mean by that? So I'm going to quickly show you a simple example. I want to do it two ways because I don't know which way you've been exposed to. You can stick with the method that you are comfortable with, okay? So we have the function y equals x cubed plus 2, okay? We want to find the inverse, okay? Fine. So we solve for x. What does it mean? Move the number 2 and take a cube. So we are moving the number 2. Whether you write y minus 2 equals x cubed or x cubed equals y minus 2 makes no difference, class. And so x becomes the cube root of y minus 2. Okay? Now you do the interchange. What do? You interchange x and y. So x becomes y, y becomes x. You're done. Just change the name from y to f inverse. And this is absolutely fine. The way I like to do it, and again, it's similar, class. You stick with the method if you're doing the homework or exam and they want you to do it in a specific order, you follow that, but I want you to be exposed to both of them. The way I do it is very simple. I start with the given and change the f of x to y. That's the first step. That's the same thing. So I do the interchanging here. In other words, right here, I change the y to x and x to y. So this is what I get. Okay. Now I solve for y. So I'm going to move the 2. That means I'm going to subtract 2. And then I take a cube root. And I'm done. I just changed the name y into f inverse. And that's it. Okay, class? Now, you really have to check your work. I haven't done it yet, so I'm going to quickly go over this for you here, okay? But I leave that normally to you. You should be able to do one of those, okay? So if we stick with one of them, let's say we are going to do f of f inverse, which means f of f inverse of x. That means x cubed plus 2. Now I'm going to use a different color. I'm going to replace this with F inverse, which is cube root of X minus 2. So what happens, it comes out as X minus 2. We have the plus 2 outside, and the final answer is X. And that's a proof we haven't made a mistake. I hope it is clear to you. All right, f of 1 is given, f of 3 is given, f of 8 is given, and we want to find their inverse. So it's very important to understand, just for the sake of argument, if you're looking at this case, if f of 1 is 5, that means f inverse of 5 is 1. That's really the meaning of it. F of 1 is 5. I want to just concentrate on that, and I'll tell you what that means. It means 1, 5 is a pair that belongs, this is an element of, okay, f of x. That's the meaning of f of 1 equals 5. So we have a pair 1, 5. Okay, everybody? Therefore, we have a comma, we have a pair 5, 1. You can find this on the graph of which function? F inverse. That's the meaning of it. As long as I know this meaning, practically I'm done. Okay? F inverse of 5 is 1, because f of 1 is 5. F inverse of 7 is 3, okay? And f inverse of negative 10 is 8, because f of 8 is negative 10. And if this is f inverse maps it back. It's very simple, okay? So take a look at what I wrote at the top and make sure you're very comfortable with what I have at the top. Then the rest becomes easy, okay? So the moment you see f of 1 equals 5, the meaning is the pair 1, 5. Okay, class? And for inverse means the pair 5, 1. That's all this. Okay, very straightforward. All right, let's find the inverse function here. This is a little bit more interesting. So what we do, we start by going through the process. The process that I like is immediately I change the name f of x to y. Okay, and then I will interchange x and y. So wherever I see x, I change it to y. Wherever I see y, I change it to x. And believe it or not, at this step, we pretty much have the inverse. This is it. This is the inverse. However, we write as y equals y as a function of x. That's why we solve for y. To solve for y, we do the cross product, okay? So if I say this is over 1, and I do this cross product, I hope everybody knows what I'm talking about, we end up with the following. So x times 2y is 2xy, x times 3 is tx, 3x, and then 1 times 4y minus 1. We're solving for y. So if we are solving for y, everything involving y comes to the same side, x to the same side. And how do you move it? It really doesn't matter. I can move this one that way and this one that way, or I can move it the other way around. In any event, I'm bringing the y's together and x's together. Okay. Now on the right side, I factor out the y. Okay, so I want to write the right side. So the right side is y times 4 minus 2x. One might say you can take the 2 out. I'm not interested in that. I want to take the y out, okay? Can I take the 2 out? Yes, and then I divide by 2 times 2 minus 2x. That's okay. That's not what I want to do, okay? And so look at the right side. It's y times the parentheses. So what do you do with the parentheses? Get rid of it. How? Divide both sides by it. So I hope you see how we go from here to here. It's a very simple process, class, okay? It's a very simple process. Now, you change the y to f inverse, and you're done. Now, the only thing I want to add, what if we moved it, if we go back to this step, class, if we go back to this step and change the way we moved things, for example, we moved 4y to the left and 3x to the right. If we did it that way, I'm going to write it down here, we would get 2xy minus 4y equals minus 3x minus 1. Which means when you get to this part, the answer looks like this: y equals minus 3x minus 1 over 2x minus 4. So I hope you realize these two are the same. The difference is this one with the asterisk has too many negative signs. That's why I wanted to avoid that. Now, I leave this for you. F of F inverse equals F inverse OF. That is, that may be a little bit challenging, but I hope you can do that, class. It's just a matter of dealing with a complex fraction. I get you started on that. Okay, I get you started on that. Let's see if we can make that happen. Let me just do this then. Okay, let's see if I can do that for you this way. It goes faster. At the very least, if you could. So what I want to do is to, first of all, let me close this. Put it in here. And let me put this one in here also, so you see the steps. Okay, so if you want to write f of f inverse, for example, here's your step. 4 times x minus 1 over 2 times x plus 3, and so now you're going to put this in here, which is 3x plus 1 over 4 minus 2x, 3x plus 1 over 4 minus 2x. And to solve this, to simplify this, I give you the one more step and I leave it for you to finish it. It's very simple. It's a complex fraction. The best course of action is to multiply the top and the bottom by LCD, which is 4 minus 2x. Okay, 4 minus 2x. So when you multiply this, okay, if you look at this one and you multiply it by this, 4 minus 2x goes away and you get 4 times 3x plus 1. And then minus 1 times 4 minus 2x. That is the numerator. The denominator, if you multiply this one by this one, 4 minus 2x goes away, you get 2 times 3x plus 1, and then plus 3 times 4 minus 2x. So now this is a simple case. I'm assuming everybody can finish that. I'm going to leave it for you to finish it. Okay. and we take it from there. Okay, class? It's just one simple step left. Okay. All right, so I practically finished that for you. Okay, so I hope everybody can do it. Just one last thing. So we went through this, and for the inverse also, and so the other thing about the inverse functions, as I mentioned, the domain of one becomes the range of the other. And the pair, I went over this concept, the pair AB is on one, then BA is on the other. In other words, AB belongs to F of X, BA belongs to F inverse. This is what I was showing you. And as a result, if we were to graph the two functions using the same set of axes, they are symmetric with respect to the line y equals x. Y equals x. Very straightforward. All right, so that's as far as inverse functions. Let's look at logarithmic functions. Now, I'm assuming you remember things here. I am giving you in this page every property you need. And it comes from the fact that the meaning of a log is simply put is about exponent, okay? And as far as we recognize that, practically we're done. So take a look if, just for the sake of argument, if I put y on this side. So take a look at this arrow, okay? That means b to the power of y. Let me just put this at top now, b to the power of y is x. So take a look at that arrow, that helps remembering. The base is very obvious. Which one is the base? Log base b. Y, the result on the other hand, on the other side is the exponent. And log x base b, x, the argument, is the result. So with that being the case, we get these properties. As an example, take a look. B to the power of 0 is 1, okay? Now, it's important that you be very comfortable with those. That's the first one. The second one says if the argument, again, this is called the argument of log class x. Is the argument of log. Okay. I discussed it common other moment. All right. So if you look at the second one here, it says when the base and the argument are the same, the answer is 1. These two refer to the fact that logarithmic functions and exponential functions are inverse functions. The next one is the product rule, the next one is the quotient rule, and the next one is the power rule. In the case of a common law, we don't write the base. The base is 10. So if you see log and x, that means the base is 10. In the case of a natural log, we use ln x. And again, remember, the moment you see ln, that means the base is e. Okay. Now take a look at the left column in green. Now we want to use those properties for natural logs. So see what happens. We get the following. You need to know all of this. Later on, we look at what's called a logarithmic differentiation class. You can't afford not to, okay? So I hope everybody is comfortable with the concept. All right. And of course, if you graph, e to the power of x looks like 2 to the power of x, 3 to the power of x, 10 to the power of x, okay? And as far as the natural log is concerned on the graph, please pay attention that at this point, you have 1, 0, and the rest of the graph depends on what you're dealing with. If you're dealing with 0 to 1. The graph is below the x-axis, okay? And that's why ln x is negative and otherwise it's above, okay? This is the change of base formula. Everybody remembers that? Because normally calculators can handle what? Common logs and natural logs. Finally, we will discuss this last piece when we delve into more calculus, okay? The curve y equals e to the power of x crosses the y-axis with a slope of 1, okay? And the same thing happens with ln x because they are inverse functions. We don't have to worry about it now, but at least it's mentioned here. Okay, let's look at a couple of very simple cases discussing logs. I'm hoping you are all very comfortable with them. Okay, I'm hoping you remember the properties we're going to use them, so we want to evaluate this. Starting with part A, well, you notice a negative in between, so we can use the quotient rule and we write it as AD over 5. So log base 2 of AD over 5, which is 16. AD over 5 is 16. And the answer is what? 2 to what number is 16? The answer is 4. 2 to what number? By the way, if it's hard to see that, you can always do this. Take a look. Right here, you can say, I don't know the answer. I'm going to say X and go with this arrow and say 2 to the power of X is 16. 16 is 2 to the power of 4, therefore X becomes 4. This is one way of approaching it. All right, what about part B? Very simple. ln x is 5. What is x? Just write the exponential, e to the power of 5. You're done. It's that simple, class, okay? E to the power of 5. Okay. So that is that. And part C, I know you have to use a calculator, but I just wanted to have a question involving change of base formula. So what is log 5 base 8? You can write it as ln 5 over ln 8 or log 5 over log 8, okay? So these two ratios, we are not saying ln 5 equals log 5, by no means. We are saying the ratio of ln 5 to ln 8 is the same as log 5 to log 8. ln 5 is a natural log, log 5 is a common log. And we go with a bunch of decimals, you see the answer. It's very straightforward, okay, class? Again, I'm hoping this stuff is easy, okay? Log base 3 of 81 or log 81 base 3 or log 81 to the base 3. However you want to call it, you have to mention the base. So one way is to say, okay, this is what, let's say x. That means 3 to the power of x is 81. 81 is 3 to the power of 4. And there you have it. So it becomes pretty straightforward, class, okay? I hope, you know, and you, of course, you come up with the answer 4, okay? What about the next one? The same thing. What is that? You can use anything, x, y, z. So let's say this is x. Then what does that mean? Because I need more room, I'm going to put it up here. And in fact, let me use a different color for that. It'd be a little bit different. So what's the answer? I don't know. Let's say 25, okay, to the power of x is 5, okay? Now 25, everybody knows is what? 5 squared. So I'm going to say 5 squared to the power of x is 5. So that means 5 to the power of 2x is 5. Okay, so what is the next step? It's very simple. Again, let me use a different color. So 5 to what power? You know this is 1, right? Set 2x equals to 1, and x becomes 1/2. What about this one? This is a common log. Common log that has 1 with a bunch of zeros. The answer is the number of zeros. If it's 0 point, bunch of decimals and it ends with 1, it's the number of decimals but negative. So the third one becomes -3 because we have 3 decimals. Okay, everybody? 3 decimals. Okay. Graphing is quickly, class. All right. Starting with lnx, everybody knows how lnx, well, we're supposed to know how it looks like, okay? So y equals lnx, we're supposed to know it looks like that. Now, x minus 2, that means shifted to the right by 2 units. So what does it do? It changes the vertical asymptote from y-axis to x equals 2. Okay, and now -1, bring it down. So it's important to see the location for this intercept is now 3, -1. Those are the shifts. So as you can see from the graph, okay, domain is from 2 to infinity, range is all real numbers, okay? And we can figure out the x-intercept. There is no y-intercept, by the way. So we can see domain is x minus, and by the way, you could even find the domain right by solving this, setting the argument larger than 0, okay? The graph indicates that, algebra indicates that. Okay, so you're done with that. What is the range? All real numbers. What is the y-intercept? We have none. What is the x-intercept? If you want to find the x-intercept, you have to set y equal to 0 and solve it. So let's do that. Okay. If we set it equal to 0 and solve, what happens? ln of x minus 2 becomes 1. Okay. How do you solve this? Whenever you're dealing with a logarithmic equation, if you have a single log and a number, you just go to the definition. By definition, x minus 2 is e to the power of 1. So e plus 2. And therefore, precisely e plus 2 comma 0, that is the location for this x-intercept class. Okay, I hope everybody's comfortable with this. There's a lot of pre-calculus stuff here we are going over, and you really need to spend some time later on going over this when you're comfortable with the concept. All right. The next topic is inverse of trigonometric functions. The way they are, none of the trigonometric functions have an inverse because they are periodic functions and none of them passes a horizontal line test and they are not one-to-one. So what do? You start working on it. For example, for sine x, we do the restriction. So if you take a look at the sine x, it is not a one-to-one function. So mathematicians have decided to restrict it as follows, from negative power 2 to power 2. By the way, why is that? Because first of all, they want to cover the whole range of negative 1 to 1, and they didn't want it to be a couple of, branches that are discontinuous. So to keep the continuity, they go from negative power 2 to power 2. Therefore, if you look at this, you see the domain is this, and the range is what? Negative 1 to 1. For what? For a sine function. And so what happens for the inverse function? The range becomes the domain of sine inverse, and the domain becomes the range. Okay? So we are looking at the inverse function. So if we write y equals sine inverse x, by definition, it means sine y equals x. So pay attention to this definition of an inverse. And so remember, in the case of a sine, x is between negative power 2 and power 2. Now, this means y is between negative power 2 and power 2. So if you want to reverse the process and if you want to graph the inverse function, it's very simple. You see these points? Let me just, this one has coordinates what? Negative power 2, negative 1, right? So you use this pair for the inverse becomes negative 1 comma negative power 2. 0, 0 remains at 0. And this point has coordinates power 2. 1. It's a parentheses class, okay. Sorry. Now power 2, 1 becomes what? 1 power 2. So if you were to graph this, notice the y equals sine inverse or arc sine x. All you have to do those 3 pairs, and that's really good enough to give us the new graph. Okay? And therefore, we are going to write their composite function is x. Now, understand what happens for this to be true, okay? For this to be true, you have to pay attention to the domain of this x. Domain of this x is this, okay? But if you are looking at this one, now you want domain of this x, and that's why you have negative 1 to 1, because sine inverse, okay, is between negative 1 and 1, okay, as far as the y coordinate is concerned. You want to pay attention to that, okay. All right, so having said that, let's move on. Let's start with something very simple. What is sine inverse of 1/2? Well, I like to write it as alpha, beta, gamma, theta, x, whatever. And now I'm going to write the definition. By definition, sine theta is 1/2. I'm assuming it's a common arc, and everybody knows the answer is 30 degrees over pi over 6. I hope you remember your basic common arcs. So one of them is pi over 6. Sine is 1/2. Cosine is the square root of 3 over 2. And the rest should come out easy because tangent is sine over cosine. Okay, square root of 3 over 3. Cotangent is the reverse. Okay, square root of 3. And the other two, secant theta. Okay. Is 1 over cosine theta. Everybody remembers that. Cosecant theta is 1 over sine theta. Cotangent theta is 1 over tan theta. So those are some basics that we know, okay? And I will give you more basics as we come across it, okay? Whenever I have more room, I write the rest of them. There are a few more I want to write. I write them in a moment. All right. The next question is asking, okay, what is tan of arc sine 1/3? There are really a couple of approaches. One of them is using a triangle. One of them is the identities. I will discuss the identities in a moment. So first you start with this part and you say arc sine 1/3. What is it? I don't know. Alpha, beta, gamma, theta. You choose. By definition means sine theta is 1/3. So now if you go with a triangle, remember sine theta is 1/3. Sine theta is what? The opposite over the hypotenuse. Everybody remembers that, right? Opposite. So if you do that drawing accordingly, this is theta, opposite is 1, hypotenuse is 3. So what is the missing side? 3 squared minus 1 is 8, square root of 8. Square root of 8 is 2 square root of 2. Therefore, you're looking for tangent theta. So what is tangent theta? Tangent theta is the opposite over the adjacent. Opposite over the adjacent. I hope everybody remembers all these basics. Otherwise, it's going to be difficult to handle. Okay. You could do by identities also. So I'm going to mention a couple of identities on the next page, so I have some room. I'll do that. In the meantime, again, you really want to go over this again to make sure you're comfortable. Same thing works out with the cosine. Cosine is not a one-to-one function. We do the restriction. And if you recall, the graph goes something like this. Remember that? But the way they restricted is from 0 to pi, again, to have a continuous function. And all you have to do, look up this point. Okay, this point, those are 0, 1, pi over 2, 0, pi, negative 1. Okay, class, so this is 0, 1. This is pi, negative 1, and the middle one is pi over 2, 0. So using those, reverse the process, and you have the graph. So I hope you see that the domain, okay, which was the range of a cosine. Remember, the range of a cosine and sine are the same, negative 1 to 1. It becomes the range here, domain of negative 1 to 1. And that's why we are going to write it this way. And I hope you know the inverse functions, just as I mentioned. The only difference is, in the case of a sine, we go from negative pi over 2 to pi over 2 to do the restriction. For cosine, we go from 0 to pi. Now, tangent follows the sine, but doesn't include the endpoints. And cotangent follows cosine. As far as secant and cosecant, some people have different takes on them, okay, class? But I like to stick with the same, that secant goes with cosine and cosecant goes with sine. Now, the identities that you need to remember, the Pythagorean identities, sine squared plus cosine squared is 1. Everybody remembers that, I hope? Okay. Now, if we divide by cosine squared, both sides, we get tan squared. So sine squared over cosine squared is tan squared. Cosine squared over cosine squared is 1. And 1 over cosine squared is secant squared. So that's another Pythagorean theorem. And if you divide by sine squared, you get 1 plus cotangent squared equals cosecant squared. So those are the identities. I'm assuming you remember them, but it doesn't matter if you don't. I went over that. So you really need to remember them now. Okay, class, I can't emphasize this enough. So those are some properties, some identities that we need to know. As far as the rest of the functions, as I said, tangent follows the sine, but the endpoints are not included because remember, tangent has vertical asymptotes. So we write it in this manner. Cosecant inverse, secant inverse, cotangent inverse. It really depends on the text. They have a different take on it, but just stick with the first 4 and you'll be fine. All right. So those are inverse trigonometric functions. This is the synopsis of that. You can look into it with more details if you like. Okay. Now we have quite a few more examples we want to look at. So let's start with this. We want to find the domain and the inverse function. Okay. To find the domain, remember, this is the argument, larger than 0. So 2 plus ln x is larger than 0. That means ln x is larger than negative 2. Okay. You get to x, you can rewrite this, or you can even, if I put the e here, I get e to the power of ln x, which is x, and I get e to the power of negative 2. Therefore, x is larger than e to the power of negative 2, which means 1 over e squared. So the domain is 1 over e squared precisely. What is 1 over e squared? It's just a number. You can look up, you can put it into a calculator for an approximation. I'm not interested in that. And to infinity. Okay. What is its first? The very first thing we do, remember, I like to interchange x and y. So as soon as we do that, we get to this. We want to solve for y. First, let's get rid of this ln. And to get rid of that, we do the same thing here. If we raise, just go by the definition, ln is equal to that. So e to the power of x equals to the argument, e to the power of x. Or you can even do this, e to the power of x, e to the power of ln. And so you subtract the two. You get to ln y. And you do the same thing again. So y is e to the power of the left side, if you will. Okay. So in other words, you can say e to the power of this, e to the power of that, e to the power of ln y becomes 1. And as you can see, this is the f inverse, and the domain for it is all real numbers, which right away tells you this is the range for the original function, y equals ln of 2 plus ln x. Now, there's a lot of logs involved here. It's important that you pay attention and you get comfortable with this class, okay? It's extremely important that you do that. Okay, let's look at more interesting questions. All right, let's start with number 41. Okay. We want to write this as a single log. Okay. So 1/3 ln of x plus 2 cubed. Okay. Plus 1/2 ln x minus ln of x squared plus 3. Let me see. That would be the answer. I need more room to go over that. So I will finish the rest. I come back to this question because I want to go to a OneNote and see if I can show you the steps. But just for the sake of argument here, this 1/3 goes here and it cancels out this one has. So in other words, this becomes ln of x plus 2. Why is that? Because that 1/3, which is the coefficient, becomes the exponent. So x plus 2 to the power of 3 to the power of 1/3. Then plus 1/2 ln x. So we will have 1/2 ln x here and minus 1/2 here. So we distribute the 1/2, okay? And so we get plus ln x to the power of 1/2. And then this 1/2, maybe I have room to the 1/2 and 2 Okay, so we put the 1/2 for ln x, okay, and then we put the 1/2 for this, okay, class. So this 1/2 makes it x to the power of 1/2 or square root of x. This 1/2 and 2, they cancel each other and they give us the ln of x squared plus 3x plus 2. Actually, we can try to have it done here. I hope everybody's following that. So what you are looking at, so these 3, when we put them together, becomes the ln. The top has x plus 2. Yeah, we can do it right here. X plus 2. And then x to the power of 1/2 square root of x. And the denominator has x squared plus 3x plus 2. Now, all you have to do, let's use a different color. Let's use this. All you have to do, replace this with its factored format, which is x plus 2, x plus 1. So x plus 2 and x plus 2 cancel each other. You get square root of x left at top, x plus 1 at the bottom. I hope it's clear to everybody. It's pretty straightforward, I hope. All right. Number 41 is really simple. Ln of x plus y plus ln of x minus y minus 10. First of all, I'm going to get rid of this 10 and put it up here. I hope you see what I'm doing, okay? Then anything with the plus sign becomes the numerator. So the answer is ln. These two have a plus sign, this one and this one. So x plus y times x minus 1. And then z to the power of 10 goes down, and here's your final answer. Okay. 41C, I want to spend a minute on that. Hopefully everybody's following that. First and foremost, I'm going to get rid of this square root and I'm going to change it to 1 power of 1/2. I hope everybody can see what's happening. So 1/2 comes in front and becomes 1/2 log of x minus 1 over x plus 1. In other words, this is equal to 1/2 log of x minus 1 over x plus 1. And finally, separate them completely. And this is the final answer. Okay, again, we're going over this pretty fast, but it's really not that big of a deal, I hope. So let's move on, class. We go to the next one, number 26. We want to find the inverse. So I want you to pay attention to this one. It's going to happen very fast and it's fairly simple. Number 1, you can interchange x and y. That's the first thing. You have all the steps, class, here, so just pay attention to what happens. So we are interchanging x and y. Of course, f of x is y. We are interchanging x and y. We are interchanging x and y. We do the cross product. I'm hoping nobody has any problem with the cross product. So this is the cross product. Okay, so this is the cross product. Fine. What is it that we are solving for? We want to solve for y. So how do we do that? We see e to the power of negative y, which means 1 over e to the power of y. You can write it as a fraction or just say, you know what, I'm going to multiply both sides by e to the power of y to get rid of the e to the power of negative y. If you multiply both sides by e to the power of negative y, my apologies, e to the power of positive y, then it becomes x times e to the power of y The next one, they cancel each other, equals 1 times e to the power of y, and then the other ones cancel each other. So I hope you see the transition. If, let me use a different color here. If you multiply this equation by e to the power of y, take a look at what I wrote in red. Then you see the next line. You're going to solve for e to the power of y by bringing everything involved in that to the same side and factor it. So e to the power of y is the right side divided by the parentheses x minus 1. Okay, now we have too many negative signs. You can keep it. If you kept it as that, it's absolutely fine, class. But the reason I'm changing because there are too many negatives at the top and the bottom. I hope you see how we can make this transition. This is a basic, arithmetic dealing with signs. And so what is y? From e to the power of y, how do we go to y? We make it into a natural log. Okay, class? We make it into a natural log. Okay. There's a lot on this page you need to get comfortable with. Okay, class, there's a lot on this page. All right, let's look at some equations. ln of x squared minus 1 is 3. It's very simple. You just change it to an exponential format. So the argument, which is x squared minus 1, is e cubed. And move the negative 1 and take a root, and you're done. It's very simple, plus minus. Part B, you have two choices, class. You can deal with it the way it is, or you can let e to the power of x be some variable of your choice, anything you want. Let me actually, let me just write it. Let me use a different color because I'm going to use a red one. It's hard to see now since. Okay, let's say e to the power of x, you choose it to be y. Therefore, you have y squared minus 3y plus 2 equals 0. Or, and that's a simple factoring, okay, which is simply y minus 1, y minus 2. Or just recognize it with the e. Whatever is easier for you. If you go with the y becomes 1, y becomes 2. That means e to the power of x is 1, e to the power of x is 2. X is ln 1, which is 0, and x is ln 2, which is precisely ln 2. You can, if you want to write the approximation, a bunch of decimals. The only thing I want you to pay attention to is the following. Both of them have answers, but for the sake of argument, if you had something here like e, just in case e to the power of x plus some number, let's say plus 5, then e to the power of x becomes negative 5, which has no solutions, okay? I'm going to erase that, but I want you to see that both of them happen to have a solution. Here's the next questions. ln, and again, you can assume this is, I don't know, y, for example. ln of y is 1, okay? So y is e to the power of 1. That means ln x is e to the power of 1. And again, do it again. ln x equals e. That means x is e to the power of e. I hope you see that. It may be too simple to see, honestly, but I hope you can see it. So one more time. If it bothers you, ln x, write it as ln of y or ln of z or any variable of your choice except x, of course. So ln of y is 1, and y becomes e. Now you replace the y with ln x, okay? So if ln x is e, then change that to an exponential form. Okay. We are solving for x, class. We are solving for x. So for part B, we are going to do the same thing. To solve for x, here's the easy way out. We divide both sides by e to the power of bx. Okay. And so the left side becomes e to the power of a minus bx, and the right side remains as a cc, some sort of a number or a constant. And we are going to change this to from exponential to logarithmic format, because we want to go to x. So you can say ln of the left side is ln of the right side. Ln of the left side becomes a minus b times x, and ln of the right side is c. In other words, what I'm saying is you could say ln of this is ln of that. That's it. So the left side, ln and e, they cancel each other, a minus b times x, and x becomes ln c divided by a minus b. Okay. Ln of 2x plus 1 is 2 minus ln x. What are we solving for? We are solving for x. Let's get everything involving x to the same side. So when we move the minus ln x, we get plus ln x. When we combine them, we get ln of x, in other words, times 2x plus 1 is 2. Okay. And how do we get to the argument? The argument x times 2x plus 1 is e squared. So when you distribute, you get 2x squared plus x. Subtract the e squared minus e squared equals 0. How do you solve for x? There is no way except the quadratic formula, class. Quadratic formula. X is minus b plus minus the square root of b squared minus 4ac over 2a, where a is 2, b is 1, and c is negative e squared. I'm assuming everybody can now come up with that minus b, that means minus b, minus 1, plus minus the square root of b squared, which is 1 square root of 1, minus 4 times 2 times negative e squared, and that's your x. There are two answers. We only accept one of them. Why is that? Well, if you go back to the original equation, this is a natural law, this is a natural law. Remember, the first one, 2x plus 1 must be larger than 0. The second one, x must be larger than 0. So if you look at the second one, which is easier to see, if you use minus 1 minus the square root of 1 plus 8e squared, square root of that over 4, that is negative. That's why there are two answers. One of them is excluded, class. One of them is excluded. I can't emphasize this enough. So you really want to see the domain of your original function. All right, we want to solve this inequality. So one easy way, in order to get to x, we can take the natural log of 3 sides. Natural log of the left side is ln 1, in the middle gives us 3x. So this is ln, this is ln, this is ln. So ln1 and ln2 are clear, and in the middle is 3x minus 1. And by the way, ln1 is 0, okay? So we move the negative 1, that means we add 1, divide by 3, we're done. It's that simple, class, okay? All right, we are going to look at the next one. The next one, 1 minus 2 ln x is less than 3, so move the 1. Okay. Divide by negative 2, so the sign flips over. Ln x is larger than negative 1. So how do you get to x? You put e here and you say e to the power of ln x, which is x, larger than e to the power of negative 1. By the way, e to the power of negative 1, of course, means 1 over e. It's a precise answer. In calculus, you like to keep it as a precise answer, okay? We want to evaluate these two functions. What's the first one again? Let's say we don't know. We say alpha, beta, gamma, x. You choose it. And by definition, sine of alpha becomes negative 1 over square root of 2. By the way, it's negative square root of 2 over 2. I hope everybody remembers that. It's the same thing. You can change it if you want to, minus square root of 2 over 2. And that's, remember, if you ignore the negative, square root of 2 over 2, alpha is pi over 4. Because of the restriction on the inverse, it goes from negative to positive. There's only one answer, and that's negative pi over 4. I hope everybody remembers the reference arc. So if you're looking for sine alpha equals negative square root of 2 over 2, first look at square root of 2 over 2, find the reference arc, and then take it from there. The second one, alpha, beta, gamma, you name it. By definition, cosine beta is square root of 3 over 2. And I hope you remember it. It's very simple. It's just pi over 6, okay? It's very simple. It's pi over 6, okay? By the way, just, to remind you, if you have something like, let's say, sine inverse of 2, that doesn't work, okay? What is that? You can say, I don't know. Let me call that, because I want you to see why it doesn't work. Let's say it's x, therefore sine x equals 2, and this has no solutions, okay? Sine x is between negative 1 and positive 1. That's why you want to pay attention to that. All right. We want to show that cosine of sine inverse is square root of 1 minus x squared. So to do that, we start with this guy. And we say, we don't know what it is. How about, again, something like theta? By definition, sine theta becomes x. Okay. And everybody remember sine squared plus cosine squared is 1. So therefore, cosine is plus minus square root of 1 minus sine squared theta. Again, I'm reminding you of the identity. You replace it with x. And you have plus minus square root of 1 minus x squared. Now we choose only the positive one. Why is that? Very simple. When we look at the sine inverse, remember the restriction is between negative pi over 2 and pi over 2, okay? Which means what? The first quadrant and the fourth quadrant. Cosine is positive in the first quadrant, and in the fourth quadrant. I hope everybody remembers that. Sine is positive in the first and second quadrant. Okay. Tangent and cotangent, positive in the first and third quadrant. What about number 72? What is sine of 2 arc cosine x? Well, if arc cosine x is theta, okay, that means cosine theta is x. And we want sine 2 theta as a result. Class, we want sine 2 theta. I hope everybody's following that. I'm basically replacing this with what we found here. So what was the identity? Sine 2 theta is 2 sine theta cosine theta. And we already know sine and cosine from the previous one. So sine is the square root of 1 minus x squared. Cosine is x, okay? And I'm going to reverse the order. I hope everybody can see how it becomes that, okay? It's very straightforward. So we should be fine with that. Now, the only thing I want to add here, so is the following. Let me see what color I want to use to make it easy to. Okay, so this comes from the fact that we did this before. So what about, so this is sine 2 theta. That's an identity you should know. What is cosine 2 theta? Cosine squared minus sine squared. 2 cosine squared minus 1. 1 minus 2 sine squared theta. There are a few more examples. You're more than welcome to look at them on your own. So this is the synopsis of this section.